The ground beneath our feet feels solid. It feels firm and permanent and unmoving. But this is not the truth of the matter. The surface of our planet, the very crust upon which we build our cities and sail our ships, is not one single piece. Instead, it is a mosaic. It is a grand and complicated puzzle made of enormous slabs of rock. We call these slabs tectonic plates. They are immense, some the size of continents, others smaller, fitting together like the sections of a turtle's shell. These plates are not still. They are in constant slow motion, drifting across the deeper, hotter, softer layer of the Earth known as the mantle. This movement is incredibly slow, often no faster than the rate at which our fingernails grow. Yet over the vastness of geological time, this patient journey reshapes the entire face of our world. These great plates interact with one another at their edges, or boundaries. It is at these boundaries where much of the Earth's most dramatic geology happens. The plates can crash into each other, a process that crumples the crust and thrusts up mighty mountain ranges like the Himalayas. They can slide past each other, a grinding, jarring motion that unleashes the shuddering force of earthquakes along fault lines like the San Andreas in California. And most importantly for our story, they can pull away from each other. This is a process of separation, of tearing apart. These specific boundaries, where the Earth's crust is stretched thin and ripped asunder, are known as diverging plate margins. They are the planet's great construction zones, places where new Earth is born from the fiery depths below. Imagine two massive conveyor belts placed side by side, moving in opposite directions. This is a simple but useful way to think about a diverging plate margin. The plates on either side of the boundary are being slowly but relentlessly pulled apart. This is not a gentle parting. It is a process of immense force, driven by powerful currents, swirling within the molten rock of the mantle far beneath the surface. As the two plates inch away from one another, a gap, a rift, is created between them. This is a zone of weakness in the Earth's crust. It is a scar on the planet's skin, a place where the immense pressure holding the world together is lessened, allowing the hot, restless interior to finally make its presence known. This pulling apart, this divergence, is a fundamental process in the life of our planet. It is happening right now, deep beneath the oceans and even across some lands. It is a quiet, hidden drama for the most part, occurring far from human eyes. But its effects are profound. It is the engine that drives the creation of new seafloor, a process that constantly renews the ocean basins. It is the reason why continents that were once joined together, like Africa and South America, now lie thousands of miles apart, separated by a vast ocean. And it is the reason for a very special and very important type of volcano. These are the volcanoes that rise from the rifts, the children of the Great Separation. The question, of course, is what drives this immense separation? What force is powerful enough to tear solid rock plates, many miles thick, away from each other? The answer lies deep within the Earth, in the semi-molten layer known as the mantle. The mantle is not a placid sea of liquid rock. It is a dynamic, churning, and incredibly hot place. Heat from the Earth's core, the planet's superheated center, rises through the mantle in great slow-moving columns. These are known as convection currents. Think of a pot of water boiling on a stove. The water at the bottom gets hot, rises to the surface, cools, and then sinks back down again, creating a circular motion. A similar, though vastly slower and larger, process happens within the Earth. These convection currents act like giant unseen engines. Where two currents rise and move away from each other near the surface, they exert a powerful dragging force on the bottom of the tectonic plates floating above. This drag is relentless. It pulls the plates in opposite directions, stretching the crust that connects them. The rock is put under incredible tension, like an elastic band being stretched to its limit. At first, it stretches and thins. The crust becomes weaker, more fragile. Eventually, the tension becomes too great for the rock to bear. It begins to crack and fracture, creating deep fissures and faults. The great pulling apart has begun. This process of rifting does not happen all at once. It is a geological event that unfolds over millions of years. As the plates continue to move apart, the valley or rift between them grows wider and deeper. The pressure on the underlying mantle is reduced significantly. This reduction in pressure is a critical step. The rock of the upper mantle is incredibly hot, but it is kept solid by the immense weight of the crust above it. When that pressure is released, the rock can finally change its state. It begins to melt, transforming from a solid, albeit a very hot solid, into a liquid. This newly formed liquid rock is what we call magma. It is less dense than the solid rock surrounding it, so it begins to rise. The journey of the plates away from each other is therefore the trigger for everything that follows. The ceaseless motion of the mantle's convection currents provides the power. The rigid crust provides the material to be torn. The result is a rift, a wound in the skin of the Earth. And into this wound, the hot blood of the planet, the magma from the partially melted mantle, begins to well up. The stage is set for the formation of new crust and the birth of volcanoes. The separation is not an ending, but a beginning. It is the start of a creative process, one that forges new land from the fire within. The drama of diverging plates is fundamentally one of creation. As the tectonic plates drift farther apart, the gap between them becomes a pathway. It is a channel of least resistance for the magma that has formed in the upper mantle below. This magma is a buoyant and insistent substance. Being hotter and less dense than the surrounding solid rock, it naturally seeks to move upwards, driven by the simple physics of buoyancy. It pushes its way into the cracks and fissures that have been created by the stretching crust. It is a slow but unstoppable invasion from below, a great upwelling of molten material that is destined for the surface. This rising column of magma is the lifeblood of the diverging plate margin. The journey of this magma is not always a simple one. As it rises, it can pool in chambers beneath the thinned crust. These magma chambers are like vast subterranean cauldrons, holding reservoirs of molten rock. Here, the magma might sit for thousands of years, slowly changing its composition as some minerals crystallize and sink. But the process of divergence is ongoing. The plates continue to pull apart, creating new fractures and weakening the roof of the magma chamber. Eventually, the pressure from the rising magma becomes too great, or a new crack provides a direct path to the surface. The magma begins its final ascent, forcing its way through the remaining crust. When this magma finally breaks through the surface, a volcanic eruption occurs. However, the nature of this magma gives these eruptions a particular character. The magma at diverging boundaries is derived directly from the mantle. It is what geologists call basaltic magma. This type of magma is very hot and has a low viscosity, which is a scientific way of saying it is very runny, much like honey or syrup. It also contains relatively low amounts of dissolved gases, such as water vapor and carbon dioxide. These two factors, its runniness and its low gas content, are crucial in determining the type of volcano that will form and the style of eruption it will have. This upwelling is not a single, isolated event. It is a continuous process that occurs all along the length of the diverging boundary, which can stretch for thousands of miles. Magma is constantly being generated in the mantle, rising and erupting to fill the gap left by the separating plates. As it erupts, it cools and solidifies, forming new rock. This new rock is, in effect, new crust. It attaches itself to the edges of the separating plates, and then it, too, is carried away from the rift as the plates continue their slow journey apart. This is the mechanism of seafloor spreading, the constant creation of new oceanic crust that paves the world's ocean floors. The arrival of this hot, runny basaltic magma at the Earth's surface creates a very specific kind of volcano. Because the magma flows so easily, it does not build up steep conical mountains like the famous Mount Fuji or Mount Vesuvius. Those volcanoes are formed by thicker, stickier magma that traps gas and explodes violently. The magma at diverging plate boundaries behaves very differently. It tends to pour out of long cracks or fissures in the ground rather than from a single central vent. These eruptions are known as fissure eruptions. The lava flows out smoothly and spreads out over large areas, creating broad, gentle slopes. Most diverging plate boundaries are found deep beneath the oceans. When this type of eruption happens underwater, the scene is quite remarkable. The cold seawater, which is under immense pressure at these depths, chills the outer surface of the erupting lava almost instantly. This creates a solid, glassy crust around the molten flow. As more lava pushes from behind, it breaks through this crust and oozes out, only to be chilled again. This process repeats over and over, creating strange, rounded shapes that look like piles of giant pillows. This distinctive formation is known as pillow lava, and it is a clear sign that a volcanic eruption has taken place on the seafloor. Over time, these repeated, gentle eruptions build up. Layer upon layer of solidified basaltic lava accumulates along the fissure. This creates a long underwater mountain range. These are not mountains in the traditional sense of sharp, jagged peaks. They are broad, rugged ridges that rise from the ocean floor. These submarine volcanic ranges are the most extensive geological features on the planet, yet they remain almost entirely hidden from our view. They are the physical manifestation of the diverging boundary, the scar of new crust that marks where the plates are pulling apart. These are the volcanoes of the Great Rift. While most of this activity is submarine, it is a powerful force of creation. The volcanoes are not singular peaks, but vast, linear systems of eruption. They are, in essence, long volcanic wounds that continuously bleed new rock onto the seafloor. This process, repeated over millions of years, has created the entirety of the world's ocean basins. Every square inch of the floor of the Atlantic, Pacific, and Indian Oceans was born at one of these diverging plate margins. The volcanoes here are not just isolated mountains. They are the factories that build the very ground at the bottom of the sea, a constant and vital renewal of the planet's surface. Perhaps the most famous and spectacular example of a diverging plate margin is, the Mid-Atlantic Ridge. This is a colossal underwater mountain range that runs down the center of the Atlantic Ocean, stretching all the way from the Arctic to the Antarctic. It is like a near-perfect mirror of the coastlines of the continents on either side, almost like a seam stitching the two halves of the ocean basin together. And well, this is no coincidence. The ridge is the boundary where the North American and Eurasian plates are pulling apart in the north, and the South American and African plates are separating in the south. It's kind of the birthplace of the Atlantic Ocean. Along the entire length of this 16,000-kilometer ridge, new crust is being formed every day. Magma from the mantle wells up into the rift valley that runs along the crest of the ridge. It erupts as lava, cools into solid rock, and becomes new seafloor. This new rock is then carried away from the ridge in both directions, east and west, as the plates continue to separate at a rate of about 2.5 centimeters per year. This process of seafloor spreading has been happening for, around 200 million years, slowly pushing the Americas away from Europe and Africa and creating the vast ocean that now lies between them. The Mid-Atlantic Ridge is, honestly, a living, breathing testament to the power of plate tectonics. The ridge is not a smooth, uniform feature. It's a rugged and complex landscape of mountains, valleys, and countless fractures. The very crest of the ridge is marked by a deep rift valley, a chasm where the crust is being torn apart most actively. It's within this valley that most of the volcanic eruptions occur. Hydrothermal vents, also known as black smokers, are common features here. These are superheated springs where seawater, having seeped into the cracked crust and been heated by magma, shoots back out into the ocean, carrying with it a dark plume of dissolved minerals. These vents support unique ecosystems of strange creatures that thrive in total darkness, nourished by chemicals rather than sunlight. The Mid-Atlantic Ridge is just one part of a global system of mid-ocean ridges that, encircles the planet like the seams on a baseball. The East Pacific Rise is another major diverging boundary, separating the Pacific Plate from the Nazca, Cocos, and North American plates. The Southwest Indian Ridge carves its way across the floor of the Indian Ocean. Together, this global mid-ocean ridge system is over 65,000 kilometers long. It is the most extensive chain of volcanoes on Earth, a continuous zone of creation that quietly and constantly reshapes the surface of our world, hidden deep beneath the waves. While most diverging boundaries are hidden deep beneath the sea, there is one place on Earth where this colossal geological feature rises above the waves. This place is Iceland. The island of Iceland sits directly on top of the Mid-Atlantic Ridge. It is, one of the most volcanically active places on the planet, because it is the product of two powerful geological forces working together. First, it is located on the diverging boundary between the North American and Eurasian plates. Second, it sits above a hotspot, a plume of exceptionally hot material rising from deep within the mantle. This combination makes Iceland a true natural laboratory for studying the processes of rifting and volcanism. The effects of the diverging plates are visible everywhere in Iceland. The country is literally being torn in two. The rift valley of the Mid-Atlantic Ridge can be walked through on dry land at a place called Thingvellir National Park. Here, visitors can see the great cracks and fissures in the earth, the visible evidence of the two continents pulling apart. The western part of Iceland is on the North American plate, moving west, while the eastern part is on the Eurasian plate, moving east. The country is growing wider by about 2 centimeters every year, a tangible and measurable expression of continental drift. This constant rifting provides easy pathways for magma to reach the surface, and the underlying hotspot provides an abundant supply of it. As a result, Iceland is home to more than 30 active volcanic systems. Eruptions are frequent and have shaped the entire landscape. The volcanoes here are mostly of the basaltic type, characteristic of diverging boundaries. They produce vast flows of runny lava that have created huge flat lava fields, as well as the gentler shield volcanoes. The 1783 eruption of the Lucky Fissures was one of the largest lava flows in recorded history, pouring out an estimated 14 cubic kilometers of lava and releasing gases that had a devastating impact on the climate of the northern hemisphere. Iceland, therefore, offers us a unique window into a world that is normally concealed by kilometers of ocean water. It shows us what a mid-ocean ridge looks like up close. It demonstrates the immense creative power of a diverging plate boundary when combined with a mantle plume. The island exists only because of this specific geological setting. It is brand new land forged in fire, a place where the forces that build the ocean floor have breached the surface of the sea and built a country. Iceland is a magnificent and dramatic exception, a piece of the mid-ocean ridge brought to light. The volcanoes found at diverging plate margins are fundamentally different from those found at other types of plate boundaries. The most well-known and feared volcanoes in the world, such as Mount St. Helens in the United States, Mount Pinatubo in the Philippines, or Mount Vesuvius in Italy, are located at what are called converging plate margins. These are places where two tectonic plates are colliding with each other. Typically, a dense oceanic plate is forced to bend and slide beneath a lighter continental plate in a process known as subduction. This creates a very different set of conditions for magma formation. At a subduction zone, the descending oceanic plate carries water-rich sediments and minerals down into the hot mantle. The presence of this water dramatically lowers the melting point of the surrounding mantle rock, causing it to melt and form magma. This magma is different from the magma at a diverging boundary. It is thicker, stickier, and more viscous, like cold molasses. Crucially, it is also rich in dissolved gases, especially water vapor, which were carried down with the subducting plate. This combination of thick magma and trapped gas is the recipe for an explosive eruption. As this gas-rich, sticky magma rises towards the surface, the decreasing pressure allows the trapped gases to expand. This is similar to what happens when you shake a bottle of fizzy drink and then open it. The pressure is released, and the dissolved gas comes rushing out in a violent spray. In a volcano, this process can lead to catastrophic explosions. The magma is blasted apart into tiny fragments of ash, rock, and pumice, which are hurled miles into the atmosphere in a towering eruption column. These are the explosive, dangerous volcanoes that build steep-sided composite cones, also known as stratovolcanoes. In stark contrast, the volcanoes at diverging boundaries are much gentler. Their magma is hot, runny, and low in gas. There is nothing to trap the pressure and cause a massive explosion. Instead of a violent blast, the lava tends to pour out relatively quietly from fissures in the ground. The eruptions are effusive, not explosive. They build broad shield volcanoes and vast lava plains, not steep cones. So, while both types of boundary produce volcanoes, the mechanics of their formation and the chemistry of their magma create two very different styles of volcanic activity: the explosive destroyers at converging margins and the quiet builders at diverging margins. The term volcano often conjures images of fiery destruction and peril. We think of Pompeii, buried under ash, or the dramatic explosions that fill news reports. However, the vast majority of volcanic activity on our planet is of the much gentler kind found at diverging plate margins. These mid-ocean ridge volcanoes are the quiet, tireless workers of the geological world. Their eruptions are rarely witnessed by humans, occurring as they do under thousands of meters of water. They do not pose a direct threat to cities or populations, with the notable exception of places like Iceland where the ridge comes ashore. Their nature is creative, not destructive. Because the basaltic lava at these boundaries is so runny, it flows easily and for great distances before it solidifies. This is why it does not build tall, pointed mountains. Instead, it creates shield volcanoes. A shield volcano has a very broad base and gently sloping sides, making it look like a warrior's shield laid flat on the ground. Mauna Loa and Kilauea in Hawaii are famous examples of shield volcanoes. Although they are formed by a hotspot rather than a diverging boundary, the principle of runny lava is the same. The volcanoes of the mid-ocean ridges are essentially countless shield volcanoes and fissure systems joined together in a long, continuous chain. The character of these eruptions is almost serene compared to their explosive cousins. Instead of a deafening roar and a sky filled with ash, A mid-ocean ridge eruption involves the quiet welling up of glowing red lava onto the seafloor. It flows like a river of fire, creating the distinctive pillow lava shapes as it meets the cold, dark water. There are no pyroclastic flows, the terrifying, fast-moving avalanches of hot gas and ash. There are no lahars, the destructive volcanic mud flows. The drama is one of silent, steady construction, a process that has been going on for hundreds of millions of years, largely unnoticed by the world above. These gentle giants, hidden in the deep ocean, are therefore the most common but least famous type of volcano on Earth. They are responsible for producing more lava than all other types of volcanoes combined. Their continuous, effusive activity is what paves the ocean floor, drives the continents apart, and shapes the fundamental geography of our planet. They are a reminder that not all geological power is expressed through violent catastrophe. Sometimes, the most profound changes are brought about by slow, steady, and quiet processes, working away in the dark depths of the sea. The volcanoes that form at diverging plate margins may be gentle and hidden, but their importance to the planet cannot be overstated. They are, quite simply, the architects of our world's surface. The process of seafloor spreading, driven by the volcanism at mid-ocean ridges, is the engine that moves the continents. Without these ridges creating new crust, the entire system of plate tectonics as we know it would grind to a halt. The constant renewal of the ocean floor ensures that the plates keep moving, crashing into each other to build mountains and sliding past each other to cause earthquakes. They are the starting point of the whole tectonic cycle. Furthermore, these volcanoes play a crucial role in regulating the Earth's chemistry. The interaction between hot rock and seawater at mid-ocean ridges drives a massive exchange of chemical elements. As seawater circulates through the hot crust, it dissolves minerals from the rock. When this superheated water is ejected back into the ocean at hydrothermal vents, it carries these minerals with it. This process helps to control the chemical composition of the world's oceans, influencing their salinity and the availability of nutrients. These vents also release gases from the Earth's interior, contributing to the balance of gases in both the ocean and the atmosphere over geological timescales. The unique environments created by these submarine volcanoes are also oases of life. The hydrothermal vents, with their plumes of mineral-rich hot water, support entire ecosystems that are independent of sunlight. Here, life is based on chemosynthesis, where bacteria and other microbes derive energy from the chemical compounds, like hydrogen sulfide, that are gushing from the seafloor. These microbes form the base of a food chain that includes giant tube worms, strange clams, and blind shrimp. Some scientists believe that such environments, protected from the harsh conditions on the early Earth's surface, may have been the very places where life on our planet first began. In summary, the volcanoes of the diverging plate margins are far more than just geological curiosities. They are the primary construction zones of our planet, the factories that produce all of the oceanic crust. They are the engines of plate tectonics, the great chemical regulators of our oceans, and the hosts of unique ecosystems that may hold clues to the origin of life itself. Though they work in silence and darkness, their influence is felt across the entire globe. They are a constant and powerful reminder that our planet is not a static rock, but a dynamic living system, constantly remaking itself from the fire within.